Hi everyone, my name is Mike McDonald. In this video, I will be unifying classical and quantum physics. I'll do that by first showing a local hidden variable for light. Next, I'll show you a model of quantum entangled photons that uses classical physics. And finally, I'll provide the empirical evidence to support the conclusions. But first, we need to do a little bit of background. We start here in 1935. The most famous paper in all of quantum physics was published. A paper so famous it is better known by the initials of its authors. It's the EPR paper, standing for Albert Einstein, Boris Podolsky, and Nathan Rosen. The title asks the question, can quantum mechanical description of physical reality be considered complete? I'll shorten that to, is quantum theory complete? A yes or no question. Einstein, Podolsky, and Rosen answered no, and they gave their reasons. It starts with a problem. Today, we call it quantum entanglement, and we'll just define that as two particles that exhibit unusual correlations for now. But back then, it was known as the Einstein-Podolsky-Rosen paradox, which you can read about here. So the question is, how does this quantum entanglement phenomena work? Since we have no explanation for it, Einstein, Podolsky, and Rosen came to the conclusion that something was missing in our understanding of quantum physics. And that something, the missing parts of the theory, became known as hidden variables. So hidden variables can explain the phenomena of quantum entanglement. Solve for x. The only problem is we don't know what x is or where to look for x, and so no hidden variable has yet been seen. You can read more about hidden variable theory here. So that's how things stood for about 30 years. No one was able to make progress on the quantum entanglement problem. That is until 1964, when John Stuart Bell wrote this famous paper entitled On the Einstein-Podolsky-Rosen Paradox. In it, he proposes an experiment known as a Bell test experiment, in which if you use quantum entangled particles, and if you get the results that quantum physics predicts, then by using his mathematical inequality known as Bell's inequality, supposedly you can prove the existence of a signal between those particles, and moreover, as you see here, the signal involved must propagate instantaneously, meaning a velocity of infinity. You can read about Bell's inequality here. So his answer to the question of how does quantum entanglement work, it's by faster than light signals. The reason we're getting those correlations of two particles is because when we measure one particle, the act of the measurement itself causes the particle to signal to the other particle what value to take. And it does so instantaneously. Experiments were done, and the high watermark of these experiments came in 2015. And we see a summary of that in this paper from Alan Aspect, where he famously says, we should renounce local realism. And in 2022, we saw the worldview endorsed by the Royal Swedish Academy of Sciences, which leads to the Nobel Prize in Physics for Alan Aspect, John Clauser, and Anton Zeilinger for, as we see here, for their experiments with entangled photons and establishing the violation of Bell inequalities. Essentially, they are vouching for the faster-than-light understanding of the universe. So that's the background. Let's summarize. There are two questions. Is quantum theory complete? A yes or no question. After you answer that, you now need to answer the question of how does quantum entanglement work for a complete worldview. Team No, the original team, Albert Einstein, Boris Podolsky, and Nathan Rosen, answered that quantum entanglement works through hidden variables. The problem with hidden variables, as we've seen, is that no one has ever seen one. Now, Team Yes, consisting of Niels Bohr, John Stuart Bell, and the three recipients of the Nobel Prize, say that yes, quantum theory is complete and that quantum entanglement works by faster-than-light signals. And we now see the two newest members, the Royal Swedish Academy of Sciences for Team Yes, and me for Team No. And this video lays out my reasoning. So the first thing I'd like to do is to show you the local hidden variable for light. The local hidden variable that no one has identified until now. Here's our jumping off point. This is the headline in the New York Times for a news article about the EPR paper. It starts, "Einstein attacks quantum theory," which is the clickbait of the 1930s. It's the second graph that is most enlightening. It says scientists and two colleagues, that would be Einstein, Podolsky, and Rosen, find it being quantum theory, is not complete, even though correct. Or as I like to say, quantum theory is correct, but not complete. So what does that mean? Well, let me give you an example. We'll do that through quantum analysis. And we do quantum analysis by taking measurements. And the way you measure in the quantum world is simply by counting. It's a simple three-step process. First, you identify an event, then you classify the event, and finally you count the event, as in 1, 2, 3, 4. So here's the setup. There are three people in the room. There's you, there's me, and there's New Guy. You and me are here to keep an eye on New Guy because he's New Guy. So let's do the experiment. Take a look at your screen. This is the first event. What do you see? We've done step number 1. We've identified the event. How will New Guy classify it? He classifies it as a vertical line. Is that correct? Yes. Is that a complete description of reality? Absolutely not. He now writes down he has counted 1 vertical line. Looking at your screen, here's the second event. He records it too as another vertical line. Is that correct? Yes, of course it is. And is that a complete description? Absolutely not. So we have recorded 2 vertical lines. And this is a horizontal line, and this is another horizontal line. So he has counted 2 vertical lines and 2 horizontal lines. Now, New Guy makes millions of observations just like these and comes to us saying, based on my millions of correct observations and the laws of nature, I have proof that the universe is in a superposition of states with itself. I think we would easily see the flaw in the argument. If you are confusing 2 different states of a system as one, then you're going to end up with false conclusions, such as a superposition of states in the universe. But let me ask you this. How about if this is what we were observing? Can we record it as anything other than a horizontal line? No, of course not. Does that now mean there really is a superposition of states in the universe? Of course not, no. What it means is that a straight line cannot represent a complete and unique state of a system. For all we know, we could be looking at the edge of a coin. We have heads on top and tails on the bottom. If we rotate that coin around the center of that line by 180 degrees, it'll still look like a horizontal line, but the heads will be on the bottom and tails will be on the top. But it'll still be a horizontal line to us. So that leads us to what I call the first law of quantum reality. A line cannot be a complete model of reality. I call it the don't be like New Guy law. So where are physicists acting just like New Guy? It's here, when they talk about polarity. It's when they describe polarity. If we scroll down on this article, we see a section on transverse electromagnetic waves, which is, of course, light. We see a depiction of such a wave to the right here. We see that this image is similar to images in first-year physics textbooks all over the world. And in this case, we are looking at a vertically polarized electromagnetic wave because the electrical field is oscillating in the vertical direction. So yes, in this case, we see the use of a straight line model. They're saying it's a vertical line. Now, this is just a wave. Photons aren't waves, they're wave particles. And in a Bell test, we are measuring photons, not waves. So how do physicists model the polarity of photons? We come to this article on the very subject matter of quantum entanglement, looking at a diagram to the right, and we see that photons are vertically polarized or horizontally polarized. That's how the modern-day quantum physicist specifies polarity. They really are using a line as a model of reality. If we examine this paper, with one of the authors being the Nobel Prize winner Anton Zeilinger, and go down a bit, we can see that he too specifies photon polarity as horizontal and vertical. They're measuring horizontal lines and vertical lines. Coming back to this article on quantum entanglement and going down a bit, we see the meaning of quantum entanglement. And it is a superposition of states. This has new guy smell all over it. So we're going to have to fix this. And we start with this. This is how I will be modeling the polarity of photons as understood by the physics community of today. It is a model of the photon as it is coming right at us. That's an imaginary circle with a diagonal line through it. The diagonal line represents the plane of polarity, and the imaginary circle represents that the line can be at any angle. For instance, this is a vertically polarized photon, and this is a horizontally polarized photon. So how did we end up with a straight line as our model of polarity? How did physicists end up with this correct but incomplete model of polarity? It comes to us from a 200-year-old experiment that we can emulate with polarizing filters. We begin with randomly polarized light. In this case, we are looking at the sky. We put up a polarizing filter. We lose half the intensity of the light. What light that does pass through the filter is all lined up just like a straight line. And we can prove it by taking a second polarizing filter and lining it up with the first and observing that we lose no light when it passes the second polarizing filter. But as we rotate it towards the 90-degree position, we begin to lose light until we hit 90 degrees and we see that there is no light passing through. The intensity of light passing through both filters is proportional to the angular difference between the two filters. This proportionality is known as Malice's law. We see it in mathematical form here. At the top, it's in its original form, and on the bottom, after it has been restated to conform with the quantum understanding of the world. In quantum theory, light is composed of indivisible particles called photons. The intensity of light corresponds to the number of photons. The probability of any single photon passing through a polarizing filter is cosine squared theta, with theta being the angle between the polarity of the photon and the polarizing filter. And since there are only two possible outcomes, the photon passes through the filter or it gets blocked in the filter, the blocked part would be 1 minus cosine squared theta or sine squared theta. And that is how we end up with a straight line model of polarity. Is it a good model? Yes, absolutely. Is it a correct model? Without doubt. You can use this model to make predictions down to the desired decimal precision. But if you ask, is it a complete model? Of course not. No, it is not. It is a violation of the first law of quantum reality. It cannot be a complete model of reality. It is impossible for this model to be a complete model of reality because if we rotate it and rotate it and rotate it until we get to exactly 180 degrees, there will be no change. This model is telling us if you do a 180-degree rotation, no change has occurred. And that, of course, is a complete absurdity. There is no possible worldview that can defend the idea that if you do a 180, you're right back where you started. And yet we are told that the polarity of photons can be completely characterized as being vertical or horizontal. So this model is incomplete. How do we fix it? How do we make a more complete model of the polarity of a photon? How can we make a more complete model of reality? Here's how I do it. I just put an arrowhead on one end or the other. That way, if you rotate 180 degrees around the center of that circle, it will look like this. It's different. And if you do another 180, it will look like this. What this new model of polarity is saying is if you do a 360, you're right back where you started. And if you do a 180, you are not. And so this model is a more complete picture of reality. This model keeps track of the orientation. This model helps to prevent confusing two different states of the system as one. So whenever we run into a situation where we use this model of polarity, a model that is correct, a model that we can make precise calculations with, and a model that is incomplete, whenever we see this symbol, we should recognize that this is the more complete model of polarity. We should recognize that there is no photon that has the polarity of the model at the top center. We should recognize that the model at the top, the current model used by Nobel Prize-winning physicists, is really a blend, an amalgamation, and an average of measurements of the two types of photons you see on the bottom. We should recognize that the models on the bottom are the real photons. And we should recognize that if we want to discuss the quantum reality of individual quantum particles, then we need to adopt this more complete model of reality. What else can we say about this more complete model of reality? We got that straight line model by taking randomly polarizing light and polarized it. We took randomly polarized photons, threw away precisely half of them, and were left with the other half of the photons all lined up at the same angle. So we start with random possibilities, and we end up with a random distribution over two possibilities. Then the outcome is a 50-50 probability. If I go up to the roof of a tall building and I open a deck of playing cards, throw them off to flutter randomly to the ground, they hit the ground and fall over, how many are face up and how many are face down? And this is as far as we can take this new model of reality. This new model of reality embraces the idea that doing a 180 does not, will not, and cannot put you right back where you started. This new model says polarity is a 360-degree proposition, just like reality. This model introduces you to a local hidden variable. A local hidden variable that was hinted at by Einstein, Podolsky, and Rosen. It is the local hidden variable that will reveal to us an explanation of the results from a Bell test experiment that uses entangled photons. Now that we have this new physical theory, how does that translate into physical reality? Where can we see these arrows of polarity? How do we reconcile this new model with physical properties? Well, everything we know about light, everything, tells us that light is a transverse quantum wave particle. That's a combination of the terms transverse wave and quantum particle. And the best way to understand transverse quantum wave particles is to create them and see how they behave. And the best way I've found to do that is to go to this website here, Wave on a String, University of Colorado, Boulder. We see one such transverse quantum wave particle here. It's a particle because it's located between here and here. In other words, it has a beginning, it has a middle, and it has an end. It's a quantum particle because you can't cut this in half and expect to see two of them. What else can we say about this transverse quantum wave particle? The polarity is in the vertical plane. So this is an example of a vertically polarized transverse quantum wave particle. And finally, what else can we say? It starts at 0 and goes up. It starts at 0 and goes up. That's different than a transverse wave particle that starts at 0 and goes down. This is an identical transverse quantum wave particle in the exact same plane of polarity, but it is physically different. So for every plane of polarity, you have exactly two types of transverse quantum wave particles. Those that start at 0 and go up, and those that start at 0 and go down. Why is that important? Because when they actually travel and propagate, they take on the shape of the wave that they have and march down the street. In this case, the leading edge is always going to be on top. And for this one, the leading edge is on the bottom, and it stays on the bottom. So let me show you my model of transverse quantum wave particles that are entangled. What did we just see here? We saw a single process creating two transverse quantum wave particles at the same time. This results in two transverse quantum wave particles that are in the same plane of polarity, and their wavefronts are on the same side of the equilibrium line. So here's the representation of my model of quantum entangled transverse quantum wave particles, of which light is one example. In this case, it's like grabbing a rope in the center, shaking it up and down, and we create two transverse quantum wave particles in the same plane of polarity with their wavefronts on the same side of the equilibrium line. In this case, we grabbed the rope and shook it up and down. We could also easily shake it down, then up. So these are two examples of quantum entangled particles. So what happens when we take randomly polarized light, we polarize it, and we grab any two photons? We don't even have to grab the two photons at the exact same time. We can grab it one on Monday, and we can grab another one on Wednesday. What are the possibilities? Well, since we do know that all of the photons are going to have the same plane of polarity, and there are 4 different possible combinations. They can have the wavefronts both on the top, or they can have wavefronts that are both on the bottom. Or they can have a wavefront on top and a wavefront on bottom, or a wavefront on bottom and a wavefront on top. These are the 4 possible combinations. So as I told you, here is my model of what quantum entangled photons are like. In this case, they are entangled. They were created by a single process at the same time. However, if we were to take any 2 random photons that happen to be in the same plane of polarity and their wavefronts are on the same side of the equilibrium line, we will not be able to tell the difference between random photons that happen to be in the same plane of polarity and have the same wavefronts on the same side of the equilibrium line from an actually entangled particles that were created at the same time by a single process. For contrast, we can take a look at what the Royal Swedish Academy of Sciences thinks is going on with quantum entangled photons. Here we see the photons being modeled as beach balls with galaxy lights. These beach balls have 9 attachment points and fibrous materials between them. The fibrous materials, supposedly, is the mechanism for the faster-than-light signals. In other words, this is fantasy. However, it's pretty much the same whenever people talk about quantum entanglement. They always have the 2 things with something weird in between them, representing that faster-than-light signal. So let's take a look at the empirical proof. Let's take a look at the evidence to support my assertions. We'll take a look at 2 experiments, and both of them involve a Bell test using photons. Looking again at this paper from Alan Aspect, he actually shows us a Bell test experiment, or at least in diagram form. This is his experiment. This is the experiment that he points to as proof that we should renounce local realism. We're going to use the results of these experiments because these are the results that they say are impossible without faster-than-light signals. They represent reality, a reality that has been experimentally verified for over 50 years. So let's take a closer look. We see 2 observers, Alice on the left and Bob is on the right. They are recording the results from measuring the polarity of the 2 photons shown above them, 1 each for Alice and Bob. The photons come from the box in the middle called the source, which emits pairs of photons. The data is then recorded as pairs. Now, in the real world, we don't use polarizing filters, we use polarizing crystals. So taking a closer look at how this experiment is done, We see that the photons will pass through polarizing crystals and be directed to one of two detectors, the +1 or the -1 detector. And each detector will send a signal to the coincidence monitor where the paired readings will be recorded. As you remember, how do we make measurements in the quantum world? We count events. We first identify the event. In this case, it's when Alice and Bob each get a detection. We then classify the event. In this case, correlated classification means that Alice and Bob both get a plus or they both get a minus. If Alice and Bob get a plus and a minus or a minus and a plus, those are not correlated or anti-correlated. In other words, they're different. There are only 4 possible combinations: plus plus, minus minus, plus minus, and minus plus. And finally, we come to Allen's diagram, which gives a 3-dimensional view. The last that our experiment needs to do is to allow Bob's polarizing crystal the ability to rotate around the z-axis, around its belly button that's being pointed to by the photon labeled nu2. We start our experiment with Alice and Bob's crystals lined up together with 0-degree difference. Lock those 2 polarizing crystals in place and turn on the source machine. We take readings until the correlation measurements settle down to a single number, and then we stop the source. We then unlock Bob's crystal, rotate it 10 degrees, lock it in place, and turn the source back on until it too settles on a number, and then repeat until we've gone through the full circle. What we're trying to do is we're trying to answer the question, what is the percent of all readings that are correlated at each and every single angle? In other words, what is the correlation probability curve? Do you remember when we defined quantum entanglement as being 2 particles that exhibit unusual correlations? Well, this is how we quantify those correlations. We use the probability curve. So let's do the first one. This one is for entangled photons, the one that quantum physicists point to as evidence of faster-than-light signals. The source is now entangled photons. So what are the results when the source is spitting out pairs of entangled photons? To answer that, we come to this article to describe Allen Aspect's experiment. Scrolling down, we see this section. The top diagram is another view of the Bell test with photons. And if we look towards the bottom left, we see the predicted probabilities of quantum entangled photons. These equations represent probabilities. They are the probabilities for each of the 4 possible measurement outcomes. P++ means the probability of seeing both Alice and Bob measuring a positive, or a +1. So the probability of seeing a plus and a plus is the same as the probability of seeing a minus and a minus, which equals 1/2 cosine squared alpha minus beta, which is your theta, the angular difference between the two polarizing crystals. And the probability of seeing a plus minus or minus plus is 1/2 sine squared theta. Remember, this is the prediction of quantum theory if you do a Bell test experiment using quantum entangled photons. So when you add the plus and minus probabilities together, you get a correlation probability curve of cosine squared theta. Theta being the angular difference between the 2 polarizing crystals. This is the quantum theoretical prediction of the result of a Bell test that uses entangled photons. We come to this paper from 1999 in which the authors are showing off a new method of creating entangled photons. Here they present their results. I like this because it shows the results of the experiment exactly as I described. After every data point is collected, the source is turned off, Bob's polarizing crystal is rotated 10 degrees, and the source is started again, all the way around for the full 360 degrees. The blue line is what quantum mechanics predicts, and the blue dots are the actual laboratory results. We see a perfect fit. Coming back to this article, we go down a bit, and we see further confirmation of the cosine squared correlations here and here. And in this case, we see John Clauser's name, the 3rd person who was awarded the Nobel Prize in Physics. This is not only the quantum theoretical prediction of the result of a Bell test, it is also what is observed in the laboratory. So we can easily elevate this equation to a fact, an undeniable, and these days an easily verifiable fact. Anyone claiming otherwise should be viewed with suspicion. This is the fact that is pointed to as proof of faster-than-light signals. So let's do another experiment. This time we're going to use photons with equal polarity. Where do we get these photons with equal polarity? We take randomly polarized light and polarize it and grab any two photons. And what we want to end up with is another correlation probability curve for this setup. So how do we do that? Well, we just use Malice's law. We can put it into a simple spreadsheet whereby we can plug in a number. In this case, we plugged in a number of 30 degrees. And we end up with a correlation probability of 62.5%. We then systematically plug in different numbers, from 0 to 90 in this case, and we plot it all out. Take a look at the curve, and we do an algebraic transformation of cosine theta. This works out to being 1/4 cosine 2 theta plus 1/2. We notice the double angle, so we plug in the double angle formula. And finally, we end up with 1/2 cosine squared theta plus 1/4. So with nothing more than a simple law of nature, a spreadsheet, and high school math, anyone can produce these results from the comfort of their own home. I encourage everyone to give it a go and verify the results for yourself. If you're more comfortable with calculus, you can go to this particular article in Wikipedia, Local Hidden Variable Theory. Unfortunately, you have to go back in time, in this case, to August of 2023. Looking down the article, we come to the optical Bell test experiments. We see a probability expression. In this case, we see Malice's law. And we also see cosine squared times cosine squared. Cosine squared is the positive, or +1. So in this case, this is a plus probability. To complete the picture, we can go easily to Desmos and make a few adjustments. We integrate over the circle from 0 to 2 pi, average over the circle, 1 over 2 pi, and then we see cosine squared times cosine squared is the same as sine squared, which is 1/8 plus 1/4 cosine squared x, the green line. So we can look at this as plus plus minus minus, and this is minus plus plus minus. These three are the red line. When you add them all together, you get the blue line of 1, meaning we've covered all possibilities. So I've given you two avenues to come up with this 1/2 cosine squared theta plus 1/4. Putting the two results next to each other for comparison, we can see that we are witnessing two different phenomena. Coming back to this article, we see a diagram to the right. Here we see the results of the two experiments plotted together. The plot uses quantum correlations rather than probabilities, but you can transform it into probabilities by moving the 0 on the left down in place of the -1. So it makes sense seeing these two equations together. These are two distinctly different phenomena. These are two different phenomena that we can recreate at will. We're told that if you apply Bell's inequality, the first result is impossible without faster-than-light signals. Therefore, these undeniable, empirically based results can only mean one thing: faster-than-light signals. But let's revisit the second experiment. Here's the model of it. We see two photons with the same plane of polarity. We can use this model and make accurate calculations and predictions. We can use Malice's law with this model as shown earlier. It is a correct model. The problem is, it's not a complete model of reality. So let's complete the model. We return to our new and improved model of polarity. The model that says if you take randomly polarized light and polarize it, you end up with two possibilities with a 50-50 split of frequency. And if you take two photons, each with a 50-50 probability, we end up with a matrix. So here are your four possible combinations and their probabilities. Very similar to these probabilities. So let's group it. Here's one grouping. 25% of the time we'll have the top pair, and 25% of the time we'll have the bottom pair. We can characterize these pairs as being in the same plane of polarity, but their wavefronts are on opposite sides of the equilibrium line. So half the time we experience pairs like this. And the other half we experience pairs like this. These pairs can be characterized as having the same 360-degree polarity. These pairs are in the same plane of polarity, and their wavefronts are on the same side of the equilibrium line. So half the time they look like this. Now when we look at this probability expression, we see that it starts to make a whole lot more sense. Let me illustrate that with a simple probability problem. We have two buckets, heads and tails. The heads bucket contains only blue marbles, and half the marbles in the tails buckets are blue. If I flip a coin and go to the bucket the coin lands up on and randomly select one marble, what is the probability that marble is blue? We take a 0.5 and a 0.5, representing how often we see each bucket, put a plus sign in between and multiply by the individual bucket probability. Here we end up with 0.75. So this probability expression makes a lot more sense now, especially if you write 1/4 as 1/2 times 1/2. This looks almost identical to the example problem. We have a cosine squared theta bucket and a 50-50 bucket. It's telling us that half the time we have a cosine squared result, and the other half we have a 50-50 result, which is wonderful. Because half the time our new and improved model of polarity look like this. And we can assign a correlation probability of 1/2 to this combination. Which leaves the other half as having a correlation probability curve of cosine squared theta, which is exactly the same as the correlation probability curve of entangled photons. So this is how you explain the results you get from a Bell test that uses entangled photons. If you use a more complete model of reality, a model that uses a local hidden variable for polarity, a variable that requires a 360-degree specification of polarity, a model that rejects the notion that doing a 180-degree rotation puts you right back where you started, then you can model the results of a Bell test with photons without faster-than-light signals. You can embrace local realism and reject the calls for renouncement. You can model a phenomenon that previously was thought to be paradoxical and render it as a combination of classical and quantum theory. And so Einstein, Podolsky, and Rosen were right. When we went from the classical world to the quantum universe, we didn't get all the pieces parts. We didn't quantize everything correctly and completely. One example of this is the polarity of an electromagnetic transverse quantum wave particle we call the photon. If we look around, we can find examples of quantum entanglement. They're everywhere. We need not refer to quantum entanglement in mystical terms. And so therefore, Einstein was right. There are local hidden variables. The universe is very real, and we've just debunked faster-than-light signals. Thank you.